So in the previous videos, we found that a naught, the first coefficient when n is equal to 0, is 1/2. Then a sub n, we had a variety of cases depending on our value of n. And then in the last case, right, we were integrating a sine wave over that period, and we got a 0 result for us. So the compact Fourier series of this pulse Wt, right, so this is our pulse Wt. It goes on and off from 1 to 0. It starts on at minus pi half, turns off at pi half. It had a radial frequency of 1 and a period of 2 pi. We can write this compact Fourier series. So using our knowledge right from chapter 2, we found the coefficients, a and bn. So now let's write this compact Fourier series where we make it a little bit more compact by making the summation using the c sub n's. So let's move on and use our knowledge to find what these c coefficients are. So the c naught and cn and the theta n. So because of the case where c naught is a naught, we know that that's 1/2. C sub n must be a sub n, and that's because our b sub n was 0, right? So therefore, the root of an, that's just going to be an, and the theta n is going to be equal to 0 because when we have the tangent of 0, we're going to have that 0 result. Now, think about this for our switching modulator. So if we were to then start putting these in, so let's write out a Fourier series. Let's write out the terms for our pulse, right? So let's write out the terms for this pulse. And our pulse, Wt, this first term, when n is equal to 0, 1/2, n is equal to 1, is we have this omega naught. When n is equal to 2, right, we had this 0 result, so there is no 2 term. The 3 term gives us this result, the 5 term, this one, and so on. Now, if we were to simplify this a bit, we could pull out this 2 over pi. And thinking back to several videos ago, now we're starting to see, right? Our original question was, how could we realize this in a circuit? Well, we just found the Fourier series coefficients for a pulse, which is basically turning something off and on. So that's not easy. That's not too easy, too difficult, right? You can put some switch in your circuit, turn it off and on. If you're able to turn your switch off and on at the frequency, at some frequency that you're interested in. So let's say you can turn your switch off and on at a frequency of FC. Well, now we're starting to get somewhere. We're starting to get to a place where we can see how you could realize a circuit that has a Fourier series coefficient terms that look just like this proposed psi of t. So our function Wt, which we just found, we're turning a switch off and on from 0 to 1. So this is just taking a circuit, right? You have a source and a switch, and you're moving this up and down. We were moving it up and down at some frequency omega naught. Well, if we were able to make this frequency omega naught, if we were able to make this our carrier frequency, then you can see that we would be getting a whole bunch of terms of Wt at our carrier frequency. So if we made our omega t, if we made that equal to our omega c, the carrier frequency, that's just the same as having an infinite series of these terms, each one at a successfully higher multiples of our carrier frequency. And then in addition to this, right, we have this DC term, but there's this one special term, right? This is a cosine of our carrier frequency. So if we make our omega naught, omega c, we're going to get a term in here that is at our carrier frequency. So this is really good, right? Because if we multiplied our message by this, then we're going to have at least one term that looks just like the proposed result that we wanted, right? Where we had this 2 pi fc. This is what we want. This is modulation. So we're starting to see that if we can make a switch go up and down at our carrier frequency, that this is going to work out very well for us. We're going to be able to make something that's called a switching modulator. So a switching modulator, where you multiply a message, turn it off and on. So you have a message multiplied by this pulse that goes off and on, which is the same thing as taking a message, turning it off and on at your carrier frequency, is going to result in a situation in the frequency domain where you have terms of this mt multiplied by wt, which are at multiples of your carrier frequency. Now, of course, right, this is the one we want, and we've already thought of many special ways to get this, right? They're all filters. So if we take our filter, pass this message times this WT through filter system, we will be able to, in the end, remove, right, all of these multiples plus this DC component, and we're going to be left with exactly what we want, this message that has been moved to plus and minus FC.